This is J.J. Thomson's 1898 plum pudding model of the atom. At the turn of the century, it was the standard baseline for atomic structure. Physicists pictured the atom as a stable, electrically neutral sphere of uniform positive charge, with negatively charged electrons embedded throughout it, like seeds in a watermelon. That model held until 1911, when Ernest Rutherford's team designed a stress test. Hans Geiger and Ernest Marsden took high-energy alpha particles and fired them at a thin sheet of gold foil. Based on Thomson's pudding model, these heavy particles were expected to pass through the soft, uniform charge with almost no resistance. While most did pass through, the team recorded a specific jarring anomaly. Roughly 1 in every 8,000 alpha particles didn't penetrate the foil. Instead, they ricocheted backward at sharp angles, behaving as if they had struck a solid object. Rutherford realized the atom wasn't a solid, uniform sphere. To make a fast-moving alpha particle bounce straight back, it had to be colliding with a concentration of mass. He concluded that the atom is almost entirely empty space, anchored by a microscopic, incredibly dense, positively charged core, the nucleus. Mapping the nucleus provided a new blueprint for matter, but Rutherford's planetary arrangement of orbiting electrons created an immediate conflict with the known laws of physics. The problem lay with James Clerk Maxwell's laws of electromagnetism. Under these established rules, any charged particle undergoing acceleration must constantly radiate energy outward in the form of electromagnetic waves. Look at the path of the electron in Rutherford's model. An electron moving in a circular orbit is constantly changing direction, which puts it in a state of continuous acceleration. Because it carries a negative charge, classical theory dictates it must bleed off its energy. If the electron is constantly losing energy, its orbit has to shrink. The mathematical consequence is absolute. Under classical mechanics, an orbiting electron would spiral into the nucleus in roughly 10 to the negative 8 seconds. Because every atom in the universe remained stable despite these mathematical predictions, physicists were forced to search for an entirely different set of laws to explain the behavior of matter at this scale. In 1913, Niels Bohr proposed a solution. He attempted to stabilize the atom by fusing classical mechanics with the emerging ideas of quantum theory. To prevent the orbital collapse, Bohr's first postulate introduced stationary orbits. He proposed that electrons could revolve in these specific paths without emitting any radiant energy, effectively bypassing the constraints of classical electromagnetism. As shown here, the second postulate dictates an electron's angular momentum must be an exact multiple of Planck's constant divided by 2 pi. The third postulate explains that an atom only emits or absorbs energy when an electron jumps from one stationary orbit to another. Bohr wasn't just adjusting the existing rules. He was suggesting that the atomic scale operates like a strict, stepwise grid of permitted states, rather than a smooth continuum. Equation 3 shows Bohr's specific calculation for the energy of an electron within a hydrogen atom. These energy values are expressed as negative numbers because the electron is bound to the nucleus. The state with the lowest, most negative energy, negative 13.6 electron volts, is known as the ground state. To move to a higher, less stable orbit, the electron must absorb a photon, whose energy exactly matches the difference between the two states. If the electron absorbs enough energy to reach zero binding energy, it breaks free from the nucleus entirely, a process known as ionization. By defining these rigid mathematical boundaries, Bohr turned the abstract concept of quantum jumps into a problem that could be tested and verified through physical observation. That verification comes from the light atoms emit. When an unstable electron drops back down to a lower energy state, it must shed its excess energy as a photon of a very specific frequency. This visual compares a standard continuous spectrum of white light at the top with the emission spectrum of an atom in the middle. While white light is a seamless rainbow, the emission spectrum consists of distinct, fragmented bright lines on a dark background. The Rydberg formula, shown at the top of this graphic, is the master equation used to calculate the exact wavelengths of those emitted photons. These spectral lines are the visible evidence of Bohr's invisible quantum leaps. Because each type of atom has its own unique set of permitted orbits, these lines function as a verifiable optical barcode for matter. The hydrogen spectrum is organized into specific named series, categorized by which energy level the falling electron lands on. Electrons dropping to the first orbit create the high-energy ultraviolet light of the Lyman series, but when an electron drops to the second orbit, the energy release falls within the visible spectrum. This creates the Balmer series, the specific colors our eyes can actually see. Transitions ending at the third, fourth, and fifth levels produce the Passion, Bracket, and Fund series, which appear in the invisible infrared region. Bohr's model has clear limitations. It fails to explain complex multi-electron atoms and was eventually superseded by models involving elliptical orbits and Heisenberg's uncertainty principle. Despite those flaws, Bohr's quantization of electron shells provided the mathematical foundation needed to resolve the stability crisis and explain the hydrogen spectrum, bridging the gap between classical motion and the quantum world.